In this video, I will be introducing our work 3D reconstruction with vast dipole sums. The problem we're trying to solve is reconstructing a 3D object from posed multi-view images. In the past couple of years, there has been tremendous progress in using neural and inverse rendering to solve this problem. In particular, one of the most influential works has been neural radiance fields, which represent the entire scene as a volume parameterized using a neural network. This representation works well for novel view synthesis, but not so much for reconstructing geometry, as it is not an actual surface representation. Later work focusing on geometry reconstruction instead model the surface as an implicit function, like an SDF. Directly representing the underlying surface greatly improves geometry reconstruction. However, the use of neural networks generally makes reconstruction slow. More recent work, starting with 3D Gaussian splatting, has shifted towards point-based representations for novel view synthesis. Together with efficient rasterization, such representations are generally much faster. However, as with neural radiance fields, these approaches perform poorly for geometry reconstruction tasks because they do not represent a surface. So our goal is to design a suitable point-based implicit surface representation. Such a representation will allow us to achieve geometry reconstruction quality analogous to neural implicits, but with efficiency comparable to Gaussian splatting. Our representation will use fast ray tracing instead of just rasterization, making it more flexible for relighting and multi-bounce rendering tasks. Let's first think about what properties a good point-based implicit surface representation should have. First, a good surface representation should allow for efficient image rendering. Second, it should be efficiently differentiable for inverse rendering, allowing gradients to propagate from the images to the points. Shifting focus to the surface itself, it should provide some level of geometric regularity. And by that I mean, if there's a hole in a point cloud, the reconstructed surface should be able to smoothly fill in the hole. And if there's any noise in the point cloud, the reconstructed surface should still be smooth. Lastly, it should be easy to initialize from point clouds available from Structure from Motion or multi-view stereo software like Colmap. A good starting point would be the surface representation of Poisson surface reconstruction. It is widely used for its geometric regularity properties, and it can be easily initialized from Colmap. It is also differentiable. However, it is not particularly efficient, and in practice it becomes very computationally expensive to differentiate through during inverse rendering. Now let's look more closely at how Poisson surface reconstruction works. Starting from an oriented point cloud, it solves this Poisson PDE to obtain an implicit surface. For the source term of this PDE, it takes each point and its normal and blurs it with a Gaussian kernel. It then uses a discrete grid and performs a global solve operation to obtain function values everywhere on the grid. Now let's consider trying to differentiably render such a surface. Given a camera, we shoot a ray, and we need to evaluate the implicit function at several points along the ray, in particular very densely near the first ray surface intersection. Even though we require the implicit function values only at these points, we still need to perform a global solve operation on a very dense grid, making rendering and differentiation very expensive. For efficient rendering, we instead want an implicit surface representation that supports pointwise queries at arbitrary points without the need for a global solve. To achieve this, we formally prove in our paper that we can compute pointwise values of the same implicit function as a sum of dipoles that we call the regularized Poisson kernel. You can find the proof details in our paper. Then, during rendering, we can compute the sums at only the points along each ray, and importantly, each sum can also be done with logarithmic complexity using an octree hierarchical structure, and I will get back to this point later. To understand this dipole kernel we use, let's first remove this regularization, in which case our dipole becomes the standard Poisson kernel. You may then recognize this summation as the point cloud Winding number. If we examine this representation more closely, we will notice that it is singular at the point cloud locations, because the Poisson kernel blows up to infinity. The singularity is problematic for ray tracing because it means rays getting closer and closer to the point cloud locations become numerically unstable. The regularized Poisson kernel I mentioned earlier is simply the convolution of the singular Poisson kernel with a Gaussian kernel, arising from the use of Gaussians to diffuse point cloud normals in Poisson surface reconstruction. This Gaussian regularization makes our implicit surface representation free of singularity issues. This singularity also creates strong artifacts when we extract isosurface meshes, for example using Martian cubes. This issue was mentioned in the original point cloud winding number paper, and our use of regularization eliminates it completely. This singularity of the winding number also forces the underlying surface to pass through all of the points. This exact interpolation is undesirable because the surface degrades quickly when there is noise or outliers in the point cloud, for example whenever we're dealing with real-world point clouds. On the other hand, even under extreme noise, our regularized winding number representation still produces a smooth surface. Lastly, to optimize this implicit surface through inverse rendering, we make a simple modification. We use a weighted sum of regularized Poisson kernels and make the per-point weights and normals trainable. The use of per-point weights also allows us to deal with noise and outliers in Colmap point clouds that we use for initialization. For example, removing outliers is easily done by optimizing their weights to 0, and we call this representation the regularized dipole sum. Finally, to summarize, suppose we initially have some noisy point cloud representing an underlying surface. The winding number produces a noisy and inaccurate surface. The regularized winding number produces a smooth but still fairly inaccurate surface. With inverse rendering based optimization, our regularized dipole sum produces a smooth surface that closely matches the ground truth. Here's a comparison of these three representations using 3D meshes extracted from them, and we see the exact same problems as we saw in 2D. Let me now explain how we use our representation to perform volume rendering for inverse rendering based optimization. During volume rendering, we sample locations along a camera ray and compute at each location the volumetric density and radiance. We use these quantities to estimate the color of the ray through the volume rendering equation. We compute the volumetric density directly from the implicit function values from our regularized dipole sum using the theory we presented this summer in our CVPR paper, Objects as Volumes. To represent the radiance or color at each ray location, we again use the regularized dipole sum representation. Even though we motivated it as a geometry representation, it can interpolate any per point quantity, including vector-valued appearance features. We pass these features into a small MLP to predict radiance and use standard volume rendering to obtain a final image. Back to a point I mentioned earlier. As we need to evaluate the regularized dipole sum for every query along every ray, it would still be prohibitively slow for rendering real-world point clouds. Instead, we can use the Barnes-Hut approximation to build a hierarchical structure that treats faraway clusters of points as a single point. This allows us to perform dipole sum queries with logarithmic complexity. In differentiable rendering, naively using AutoDiff to backprop gradients would still result in linear complexity even with the Barnes-Hut approximation. We explain in our paper how we develop a new algorithm to achieve logarithmic complexity also during backpropagation. Now let's look at a few 3D reconstruction results and compare our method with two recent alternatives: a neural method, News2, and a point-based method, Gaussian Surface, all of which take 5 to 10 minutes to produce on a GPU. In several cases, simply using the regularized winding number before any optimization produces results on par with the other methods. Our regularized dipole sum further improves the reconstruction. Importantly, our method helps prevent structural artifacts common in other methods thanks to its geometric regularity properties. In other cases, the regularized winding number produces a low-quality initial surface, which our method then greatly improves through inverse rendering optimization. I will show one more example to again highlight the importance of geometric regularization. Powerful methods such as NeuralAngelo, while taking several hours to train, can still fail to produce a meaningful surface when few views are available. This is in part due to their inability to disentangle appearance and geometry because of the lack of geometric regularization. By contrast, our method produces accurate reconstructions within 10 minutes. The project website includes our code and interactive visualizations for many more results, including results that use shadow rays. Thank you for your attention.